Okay, this is going to be the test review for the Unit 3, Topic 1 assessment, Introduction to the Unit Circle. So take a minute, pause the video, read and try numbers 1 and 2. So we are told that the gravitron makes a complete rotation every 30 seconds, and that's an important fact. And I'm just going to real quick think to myself, okay, that means the gravitron moves 360 degrees in 30 seconds, which means it's moving 12 degrees per second. That's an important fact I'm going to need. From the starting point, how many seconds will it take for Mr. Davis to be at the point closest to the wall? So we are looking for the point right here. So right there, well, let's see, if it's 30 seconds all the way around, that means here is going to be 15 seconds, which means this is 7.5 seconds. 7.5 plus 15 means that this is 22.5 seconds. Mr. Davis thinks he will be at the same distance from the wall after 100 seconds as he was after 10 seconds. Is he correct? Well, it's important to note that these times, 100 seconds and 10 seconds, are not at these nice, 90-degree marks where I can just look at it and know. So I think I'm going to write an equation. I know the radius is 30. I know we are moving 12 degrees per second. And the center is 60 feet off. And remember, we're using sine because if here's the angle, we are looking for this height. We know this is 30, and we would set up the sine of the angle equals h over 30, and the angle is determined by 12 degrees times however many seconds. So again, if we had sine theta equals h over 30, h would equal 30 sine theta, where theta is the number of degrees you have rotated. So here we go. If I do 30 sine, well, 10 seconds would be 120 degrees. And 100 seconds would be 1,200 degrees. Get my calculator. I'm going to use the Desmos calculator because I think that's what most of you are using. So 30 sine 120 plus 60 and 30 sine plus 60. And you can see that both of these are exactly the same, 85.98. And that's also my justification. An airplane is flying overhead. Oh, and here it is. I'll go through it. I might recycle the picture though, because it's so beautiful. An airplane is flying overhead. Your line of sight to the airplane is 1,000 feet. The line of sight makes an angle of 75 degrees with the ground. So you can see I drew a picture. Here is my angle, 75 degrees. My line of sight is 1,000 feet. I am looking for how high it is above the ground. So I am using sine of 75 equals y over 100. And I multiply both sides by 1,000. And I get 96 feet. Okay, so take a moment, pause the video, and read and try this problem about Jack and the merry-go-round. Okay, you should have paused the video and worked on it on your own. And the first question is, what is the shortest distance between Jack and the wall when the merry-go-round starts? Well, obviously, it's this distance right here, which is, oop, that's yellow, 60 feet. Meters, 60 meters. What is the closest distance from Jack to the wall? Well, if I take those 60 meters, center to the wall, and I subtract the radius, I get 30 meters. The furthest distance would be up here. So 60 plus 30 is 90 meters. From the start point, the merry-go-round rotates 70 degrees clockwise to point A. How far is Jack from the wall? So if I go, I'm going to set this up here. I've got 70 degrees. Pretend that's a right angle. 70, I know this is 30. I'm looking for this height. So again, it's going to be sine because opposite over hypotenuse. And I'm going to multiply both sides by 30. And whatever I get from this, I'm going to need to add 62. So I'm going to grab my Desmos calculator. I'm going to go 30, clear that out. 30 sine 70 plus 60. And I get 88 point, nearest hundredth, 80.19. Okay. Letter E, what other angles of rotation result in being the same? Less than, so if we're up there, if we want to be the same distance as 9 is the 70 degree, we want to be over here. That would be the same distance. So if you imagine this like a standard position angle that has a reference angle of 70 in the second quadrant, it would be 110 degrees. So we have the same merry-go-round as the number 1, and we're told that this merry-go-round now is making one rotation every 75 seconds. So slight change in speed, I believe. From the start point, how many seconds will it take Jack to be the furthest point from the wall? So if it's 75 seconds to go around, half of 75 is 37.5 seconds. And then half of that would be 18.75 seconds. And then let's see if I do 18.75. Oh, the furthest point, I thought it was the closest point. No, the furthest point is 18.75 seconds. So Jack's distance from the wall. So this 25 seconds, again, is not a nice north, south, east, west. It's not like a quadrantal angle here. So I'm going to figure out, all right, well, 360 degrees divided by 75 seconds. I'm actually going to grab a calculator for this, and I see that it actually is exactly 4.8 degrees per second. So I know my equation would be y equals 30 sine 4.8, sorry, t plus 60. So for 25 seconds, I'm just going to go 30 sine 4.8. Oh, whoops, too quick with the parentheses there. Times 25 plus 60. 30 sine 4.8 times 25. Close it, plus 60. And it is in, what does it want? To the nearest, do I have a rounding point here? I don't. I'm just going to go to the nearest hundredth because that's what I did last time. So 85.98 meters. So Jack thinks he will be the same distance at 125 as he was for 25. So again, just like before, I'm going to use my equation. I know this is my distance for 25. So I'm just going to do 30 sine. I'm going to put that in my calculator, and I get, actually, I'm using my calculator, my physical calculator, and I'm getting 34.02 meters. If you need to see that in Desmos, 30 sine 4.8 times 125, those parentheses plus 60. Yep, there we go. So that's not the same. No, he is not. Sorry, Jack, you are wrong. A kite string is 50 feet long and is fully extended from the ground. The top of the kite is 20 feet above the ground. Oops, that's okay. So here's the kite. To the nearest degree, find the measure the angle the string makes with the ground. So I'm looking for this angle theta, and because 20 is opposite theta and 50 is the hypotenuse, I'm going to say the sine of theta equals 20 over 50, which I know is 2/5. So on my calculator, I'm going to do the inverse sine of 2/5. If you're on a TI, you're going to do that by going, make sure you're in degree mode. Second, sine 2 divided by 5. And I can see it to the nearest degree is 24. And on Desmos, inverse sine, also 24 degrees. All right. So we have a different merry-go-round. This one's a little smaller. It has a radius of 20 and it is 40 meters from the wall. And now we are moving one full rotation in 45 seconds. So the first thing we are being asked to do is, what is Jim's distance at 30 seconds? So 30 seconds, you know, is not a nice fourth of 45 seconds. And I have an equation. That's so exciting. I was gonna have to write one, but now I don't have to. So now I can just drop. So let's see, 40 plus 20 sine 8 times 30. I'm going to grab my calculator to the nearest hundredth. That's 22.68 meters. Now, the owner of the merry-go-round wants to make it more exciting because 45 seconds, slow. He wants to double it. So let's think for a second. Here, this 8t means that it's 8 degrees per second. So if I am doubling the rotational speed, this is the number I'm doubling. So I'm going from 8 degrees per second to 16 degrees per second. So my new equation will be y equals, or d equals 40 plus 20 sine 16t, because I'm doubling the speed and 8 is the speed in degrees per second. Oh, I get to draw a picture. So I've got some water. And there's a cliff. We'll pretend this is the cliff. And there's an observer. And the observer can see a ship. It's a boat. I can't draw ships. I can only draw little boats. The angle of depression to the ship is 15 degrees. So what I actually need to do here is I need to add in another line to my picture because I need the horizon sight line. So here's like my horizon line. And here is my angle of depression, 15 degrees. Now my cliff is 200 feet up. Now, because this makes a parallelogram, or in this situation, a rectangle, I know that this distance is also, I mean, like we're off a little bit because I drew the picture, but basically this is also 200 degrees or 200 feet. How far is the ship from the base of the cliff? And again, because this is a rectangle, this distance x is the same as this distance x. So I'm going to use tangent because I have 15 degrees, I have 200 feet, and I have x. I don't care, nor do I know the hypotenuse. So I'm going to say tangent of 15 equals 200 over x, put my tangent over 1 and cross multiply. I get x tangent 15 equals 200. Divide both sides by tangent 15. Grab my calculator. And I find out that the ship is, to the nearest foot, 746 feet. So we have another merry-go-round. This merry-go-round is 40 meters from the wall and has a radius of 30 and moves one rotation every 60 seconds. And now we actually want an equation. So here we go. I've got distance equals radius, sine, and I need the speed. So 360 degrees divided by 60 seconds gives us 6 degrees per second. So 6t plus 40. And again, this comes from if you have the angle here, theta, and we have a height, and we know this is 30, sine of theta equals h over 30, multiply both sides by 30. 30 sine theta plus 40 is the total distance from the wall, and then theta is the degrees traveled. If we take the speed in degrees per second and multiply by the total number of seconds, we will get the degrees that you have traveled. So if we want to know, so there's a typo here. It shouldn't be from the starting point. It should be from the wall. And 2 1/4 rotations, this is just going to be coterminal to a quarter. And so because 2 1/4 is the same as 1/4, it's just going to be 40 plus 30 is 70. And I apologize for that typo. It's a little confusing. Right, complete each statement. Got the degrees symbol. 50 degrees is in the first quadrant. It has a Y and an R. So what else has that same Y and R? Well, if I put 50 degrees, ooh, that's ugly. In the second quadrant, this angle in standard position, well, if this is 180 and I didn't go that last 50, this is 130. And then because this is Y over R and this is Y over R, and then here we've got a negative sign, which means we're gonna have to have a negative Y over R. We put 50 degrees in the third quadrant because this is negative Y. So now 180 plus 50, this becomes 230. And then same thing, another negative Y here would be 360 minus 50 is 310. 7b is similar, but now we have a negative, and then there's this sign of 280. And remember, 280 is going to fall in the fourth quadrant with a reference angle of 80. And it has a negative y. So when we have this statement here, negative y over r, we're really looking for y over r as the full statement. So here, because the second blank just has sine of an angle, we want a positive value. So if I do sine of positive 80 in the first quadrant, I'll get that same y value, though obviously my picture is super terrible. Same thing here, if I put 80 degrees in the second quadrant, I will get the same y value as the first quadrant, the opposite value of the fourth quadrant, and this would be 100 degrees. Now, to get another situation where the negatives cancel it out, I need to put 80 degrees in the third quadrant. And then that would be 180 plus 80 is 260. A circle is on the coordinate plane and its equation is x squared plus y squared equals 100. We need to remember that x squared plus y squared equals r squared is the equation of a circle that is centered at the origin. And so since r squared is 100, obviously the radius is 10. I'm told that theta is in standard position and it passes through -8, 4, 5, 6, 7, 8, -6. So here's the point. Is that it? Yeah, that was good. I'm not drawing the circle, honestly, because I can't draw a circle, even with a circle tool. Like it's, well, maybe I could. Nah, I'm not. I know the radius is 10 of my circle. Pretend there's like a circle here. So here is angle theta, which is the first thing we are asked to do, is to sketch angle theta, check. Sine of theta, we want to remember that sine of theta is y over r. The y value is -6. The r value is 10. I'm going to reduce my fraction. Oops, let's get 5. What is the measure of angle theta? Round your answer to the nearest tenth of a degree. So you want to be super careful here. I don't want to do, and I'm going to show you why, the inverse sine of -3/5, because I get a negative angle, and a negative angle comes down from the x-axis, and it's kind of awkward. So what I want to really think about this as inverse sine of 3/5, and that's 36. I want to think about this as a positive 36.87. So I did the inverse sign of actually remember this. And I got 36.8, I think it was 8.7. Was it 8.7? What's good memory? So what that is that's my reference angle. So this is 36.87. So what is theta? Theta is going to be 180 minus that. So you can see if that was a negative angle, that might be a little confusing with the arithmetic. There. And that does, whoops, I don't know why I just said minus, I'm going to say plus. So 180 plus 36.87. And that makes sense. 216.87 is in the third quadrant. Oh, 1/10 of a degree. Pay attention to the rounding, woman. So 216.9 degrees. All right, so for each problem below, we have a coordinate. It's the angle and sandwich. Okay. So I'm worried that if I draw it in the middle, I'm not going to have enough squares. I'm going to draw it like off to the side here because if I'm going negative, negative, I really only need the third quadrant. So I'm just going to draw it like boom, boom. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 3. All right, so there's my terminal ray. Okay, negative 12, negative 3. So what I need is I need the radius. And I also need to remember a couple things. I need to remember that sine of theta is y over r. Cosine of theta is x over r. Tangent of theta is y over x. So here we go. Pythagorean theorem time, just like from this equation up here. X squared plus y squared equals r squared. X squared plus y squared equals r squared. So ooh, that's a bad looking r. So I've got 144 plus 9 equals r squared. So I get r squared is 153. R is the square root of 153. So here we go. Sine of theta, y over r. Cosine of theta, x over r. Tangent of theta, y over x, and this I can reduce, so make sure you make it 1/4. Ta-da. So if you haven't paused the video in a while, it's a good time to pause the video and go find the r values for b and c, and then the sine, cosine, and tangent for b and c. Hopefully for B, I'm not going to sketch this out. I mean, this is X and this is Y. And obviously, if I go 15 squared plus 0 squared equals R squared, I get an R value of 12. So this is going to be a quadrantal angle. Like if you were to sketch this, and I'm not going to do this to scale, if we say this is 15, 0, I have 0 degrees. Sine of theta, Y over R. Whoa, why did I write a 12 here? It should be 15, dummy. Is 0. Cosine of theta, X over R. Tangent of theta, Y over X. And then our last one, same thing, X squared plus Y squared equals R squared. 25 plus 64 is 989. So R is the square root of 89. You don't even really need to sketch this. I mean, it's in the fourth quadrant, like right 5 down 8. I mean, you can if you want. But Y over R, X over R, Y over X. So X is 5, and I don't have to worry about reducing these, and that's exciting, and just double check. No, it does not reduce, and that's it. Again, make sure you can do this, not just following along with me. Print yourself off another copy of the blank notes and work on it until you can do it all by yourself without any assistance from the video, from the answer key, from your old notes.